Hi, welcome to Modern Optimization Methods. Today we will introduce the last part of Chapter 9, applying augmented Lagrange method to solve L2 loss SVM. Now, recall that we are considering the L1 loss SVM, which is we try to minimize a quadratic norm of omega plus a non-smooth function PS, okay? And meanwhile, we have some equality constraints here. So to solve this problem, we apply the augmented Lagrange method. So for the augmented Lagrange method, recall that the main focus in the method is how to solve the subproblem. So we listed 3 key points when solving the subproblem. So in the previous part, we talk about how or what is the key points to solve the subproblem. Next, we will address the key points one by one to show how we tackle them. Now, let's take a look at the first one, how to calculate the proximal mapping. So recall that the function PS takes the following form, where it is basically the sum of the max function here, okay? So the proximal function is actually the optimal solution for this minimization problem. So this minimization is actually called the Moreau-Yostar regularization, okay? So we basically, given a vector z, we are trying to minimize the distance between z and s, then plus another function ps, okay? So for this problem, in order to get the optimal solution, we can actually transfer this problem into the number of m-dimensional problem into the number of one-dimensional problem, okay? And it is basically a quadratic minimization problem for one variable. Then after that, we can discuss that due to different cases, we can actually get different optimal solution values. So this leads to the proximal formula for this function. And then we tackle the problem 1. Now, let's take a look at the subdifferentiable of this proximal mapping. This is in prepare to derive the generalized Jacobian, okay? So the subdifferentiable of this proximal term is actually some matrix which is diagonal matrix, okay? So the diagonal elements mu actually the sort of generalized gradient of max function, okay? So if you can see that if zi is greater than some constant, then it is 1. If it is between 0 and a constant, then it is 0. And if it is smaller than 0, it is still 1. All right? So between zi in 0 and this constant, it is 0. So when zi reaches this point, say zi equals 0 or cm, then the subdifferential will be a interval mu I here, okay? And we demonstrate the figure of proximal mapping in the left-hand side, okay? So compared to the traditional L1 norm proximal mapping, it's kind of shift between the L1 mapping to this one, okay? So this is the demonstration for proximal mapping as well as how we derive the subdifferentiable of the proximal mapping. Now, let's talk about how we can get the generalized Jacobian of the gradient phi, okay? As we mentioned in Chapter 6, the generalized Jacobian is actually difficult to obtain if you got very complicated functions. However, by chain rule here, we can actually identify a larger set of generalized gradient, okay? In other words, when multiplied by a vector h, then the generalized Jacobian of phi can be characterized by a larger set. We call it a generalized gradient hat, okay? We can characterize this part, all right? For this larger set, the formula is like this, okay? We got a constant matrix, which is identity, plus a constant matrix as well. Then the third part is a set, okay? Because there is a subdifferential of the proximal mapping, which we have discussed before, all right? So by doing like this, we can characterize the generalized Jacobian as well. Now, we give the globalization of semi-smooth Newton's method, okay? We actually introduced this globalization version in chapter 6, okay? So here we just copy this algorithm here to apply it to solve our subproblem, okay? So the basic idea is that we apply the line search strategy, where the step alpha k is provided by the backtracking strategy. The search direction dk is obtained by semi-smooth Newton's method here, okay? So when we apply semi-smooth Newton's method to get the direction, we have two issues to pay attention to, okay? The first one is that this matrix V must be selected from this larger set of generalized Jacobian, all right? So recall that we got this hat to denote a larger side of generalized Jacobian of phi. So we choose V from this set. The second issue is that when we solve this direction D, we need conjugate gradient method. We did not solve it directly. However, we apply the iterative solver conjugate gradient method to solve it in order to save computational cost. We will talk about this later for this issue. Now, we take a look at how we apply the conjugate gradient method to solve this linear system. The aim is that we try to reduce the computational cost, okay? Notice that this V takes the following form, all right? So this is one element from the generalized Jacobian set. And we actually, if we save this V explicitly, then we need a lot of memory cost as well as computational cost because you got a matrix multiplication here, all right? Therefore, a practical way is that how we can calculate this VH directly instead of save V and then do calculation, okay? So we do this VH calculate directly, okay, instead of saving V and do VH, all right? So if we calculate VH by this formula, then we can see that the main part we need to worry about is this one. So there is an identity matrix minus the diagonal matrix. And notice that this mu is either 0 or 1. So in order to save our computational cost, we need to find a way to make sure that this part contains as much 0 as possible. So how can we choose this? Then we can actually, for this mu, if it is 1, then the difference of this part will be 0. Therefore, we need to choose mu as many 1 as possible. All right? Therefore, we use this part. This IZ actually denotes that Zi between 0 and this constant. In other words, if Zi lies in this interval, then mu will be 0. All right? In other words, if we make difference of this part, then this will lead the index of B in terms of this row for the and transposed by this B in terms of the row here. Alright? So we can measure how small this IC is. If it contains small elements, then we can save a lot of computational cost. Now, in this table, we actually summarize different ways of computational cost. So the third way is actually what we use in our implementation. We can see that the computational cost can be significantly reduced from the previous one to here, okay? So if IC is smaller, then we save more computational cost, all right? Now finally, let's discuss the convergence result. So for the global convergence result, we use the theorem in this paper, and we can see that finally, under the settings here, we can guarantee that the sequence of omega k and sk will bounded and converges to the unique optimal solution of the original problem. Okay, so this is actually sort of global convergence result. Next, to present the local convergence result, we need some stopping criterions. So here I present different types of stopping criterions. However, I will not go to details to show why they come and how we implement it. Okay? We use these stopping criterions to get the following convergence result for augmented Lagrange method. Okay? So the first result is that the sequence lambda k will converges to lambda star, which is one of the augmented Lagrange multiplier. Moreover, the iterations here, the distance of lambda k plus 1 to omega will bounded by the distance of the previous iteration to omega. Okay? And this bounded constant beta k will tend to a constant which is smaller than 1. Alright? In other words, the augmented Lagrange multiplier has the linear convergence rate. If we have more conditions on the stopping criterion, then we can get that the update iteration omega k will also enjoy the linear convergence rate. Okay, so here this beta k is actually a constant which is related to k, and it will tend to a constant which hopefully to be smaller than 1. All right? Now, finally, let me present some numerical results. So here, we also compare our method with the state-of-art solvers LibLinear, and we compare with the DCD method, okay, dual coordinate descent method. So these are the CPU times, and these are the accuracy, all right? So as you can see that our algorithm is a bit faster than the DCD method, and in many cases, we will return a bit higher accuracy than DCD method. In particular, there are several examples showing that the augmented Lagrange method can actually significantly improve the algorithm of DCD method because it gets much higher accuracy than DCD does. Okay? Now, finally, let me conclude this part. We basically introduced the augmented Lagrange method to solve the L1 loss SVC problem. If you are interested in this part, you can download the reference here to see more details. Finally, for the chapter of this part, let me conclude in the following. So we introduced the quadratic penalty method, exact penalty method, as well as augmented Lagrange method to solve constraint optimization problem. We also present two examples to show how we can apply efficient method to solve the modern optimization problems. Okay, so this is the end of this course. Thank you. Goodbye.